Good afternoon. Welcome to Transfer Phenomena in Bioprocessing Week 5, Lecture 3. So, today we will discuss about the hydrodynamics of laminar flow in the packed bed and the Kozeny-Carman equation. So, the end of the lecture, what we are going to learn here, explain the role of the liquid recycle, then external aeration to improve the performance of the packed bed bioreactor, the first one. The second one is they describe the hydrodynamic characteristics of laminar flow through packed bed. There is a two flow is there, one is the laminar flow, other one is the turbulent flow. So, we are going to talk about only here first laminar flow, the next class we talk about the turbulent flow. So, it includes void fraction, there is a hydraulic radius is there, interstitial velocity, then the specific surface area, and how to derive and apply the Kozeny-Carman equation to estimate the pressure drop in laminar flow through packed bed. So, then finally, they evaluate the effect of the bed structure, then particle properties, and what are the operating conditions on permeability, pressure drop, then reactor performance for the engineering design. So, today we will discuss, we will learn all this one. So, first what is the liquid recycle in packed bed reactors? So, here you can see packed bed catalyst particle loaded here in the packed bed column, and there is a pump. You always pump the liquid here, then recirculated here medium here. So, this is there is stirrer is there, then sporger, and the air we are passing here, of course, the gas exhaust are there. So, why you want to recycle? So, the liquid recycle improve the mixing, then complete flow distribution here, of course, then sometimes the heat removal and to increase the mass transfer. So, mass transfer is the increase the concentration driving force. So, same way for mixing also will improve. So, what are the advantage of recycling here? The first one is for if you do recycle, then we get the uniform substrate concentration. Then of course, the channeling will be reduced, because when you do recycle, sometimes channeling directly occurs here. So, you always try to avoid the channeling, it is reduce the channeling. Then of course, we will get a conversion, higher conversion, whatever not reaction completed, and then if you pause again recycle, then the conversion definitely will increase that one. Then the better temperature control, there is a temperature control is there, you get a better temperature control, and of course, we can always use the catalyst utilization, we can improve the catalyst utilization. So, what the typical configuration here, the figure here, first starts feed tank, then pump, it goes to pump, this is a feed tank, then pump, then the packed bed, and this one is a packed bed here, then there is a separator, then again we are doing for recycle this process, this is a recycle here, it is a continuous process, it is a recycle here. So, if I ask what is the industrial example here, the immobilized enzyme reactor for glucose isomerization commonly employ this type of recycle ratio between 5 to 20. So, they made that one, the one of the best industrial example for recycling the packed bed reactors. So, then why we want to discuss about the aeration in the packed bed reactor. So, there is a two aeration, one is a direct aeration and another one is the indirect that one. But normally, generally the direct aeration is generally avoided in the packed bed reactors. So, in the packed bed bioreactors, the void space between the packing material are relatively very small or relatively small. Then when air is introduced directly through the sporger, there is a sporger, and if you introduce the air directly, and of course, the gas bubble cannot move uniformly through these narrow passages. So, then what happened? So, instead of bubbles, definitely if you pass direct aeration, then the bubbles merge together, it makes us a large bubbles. Of course, then form as a gas pockets within the bed itself we form as a gas pockets, and of course create the preferential flow channels. There is a channeling, then maybe here, okay, some separate channeling will be there, where gas bypasses the most other reactors. So, the direct aeration generally we avoid in the packed bed reactors. So, then aeration packed bed reactor, but the direct aeration generally avoid the packed bed reactor because it disturbs the uniform distribution of the liquid phase. Then reduce the effective contact between the microorganism, substrate, then oxygen. That is another aeration is generally to this one. Then as a result here, the oxygen transfer become as a non-uniform. It definitely leads the lower substrate conversion because we will not get a good substrate conversion here, and of course reduce the microbial activities, and then if your microbial activity reduce automatically, then the reactor productivity also automatically get decrease here. So, then always we go for the preferred aeration strategy here, because instead of directly you are passing to packed bed, you can always use some separate external aeration vessel, then we can do the aeration here. So, the oxygen rich liquid is then pumped through the packed bed reactors, where dissolved oxygen is transferred efficiently to the immobilized cells. That is one. So, what are the advantage of external aeration? So, when you want external aeration, of course, our advantage is more compared to direct aeration. It is a uniform dissolved oxygen condition. Wherever the disadvantage in the direct aeration, that will be a advantage of external aeration. So, the uniform dissolved oxygen concentration throughout the reactors. So, no bubble accumulation or gas trapping within the packed bed here. Of course, if you external aeration definitely is a prevents the channeling and make sure that one ensure the uniform liquid flow there throughout this one. And if you do external aeration, and definitely the stable pressure drop across the bed will be there. So, then in the case, then automatically it's improve the oxygen transfer efficiency without disturbing the packing here. So, it's enhance the substrate conversion, then the product yield also. It provide stable long term reactor operation, especially for immobilized cell and enzyme systems. So, what are the application here? It is aerobic enzyme reactors or immobilized microbial reactor, these all we will use for the external aeration. So, these are the advantages for if we use a external aeration, we will get a uniform dissolved concentration, then definitely no bubble accumulation, it will not get collapse that one, and channeling definitely it is a prevent here, and then efficiency automatically increase. These are the advantage of external aeration. So, what are the key takeaway here? What we discussed so far, the packed bed reactor contain stationary immobilized catalyst through which the substrate flows continuously here. Of course, they provide a high catalyst loading and then low shear stress, that is shear stress will be a low shear stress, and we will get a continuous production the efficiency way, this one. So, mainly the reactor performance mainly depends on the mass transfer and then residence time and pressure drop, then bed porosity. These are the variables for mainly the packed bed reactor. It is dependent on mass transfer and how much time the residence time staying inside, and of course, the pressure drop is the main role here. Then for the finally the bed porosity, these are the variables here. So, definitely liquid recycle improve the flow distribution, then the conversion efficiency also. So, the direct aeration generally avoid because we already discussed there is a channeling occurs, and then gas pockets, the channeling, it's all to reduce the reactor performance. So, what are the major industrial application here? It's definitely used for enzyme catalysis, then pharmaceutical manufacturing industry. So, sometimes for amino acid production, the wastewater treatments, then bioseparation. These are the application for this one. So far we discussed that one. Now we will discuss about the flow in packed bed. How the flow is in the packed bed here. So the packed bed is a stationary and an assembly of discrete of solid particle. There is a solid particle through which the fluid, whatever liquid or gas, it flows via void space. There is a packing material is there and there is a void space. Through that one the liquid flows, liquid or gas here. So the particles remain fixed here. See, that is the difference between fluidized bed and packed bed. The packed bed, the particle remains fixed inside the throughout the operation while the fluid continuously through the bed. So packed bed are most extensively employed reactors and then separation configuration also in chemical, biochemical, then pharmaceutical, environmental, food engineering. Because very simplicity is very simple and we can always use the high surface area and we can excellent catalyst utilization we can do here. So that's the reason packed bed we always defined as the porous medium composed uniformly the packing solid material, solid particles that provide a large interfacial area for the fluid solid interaction, so that we can enable the simultaneous transport of momentum, heat, mass. So the packed bed system we can do here heat, mass, momentum, all three together here. So there is a heat transfer taking place and there is a mass transfer also and there is a momentum transfer also. So all type of transfer taking place in the inside the packed bed. So then unlike pipe flow, normal pipe flow, it's just like that will move here. The fluid does not move through the single conduit because it follows numerous pathway. It's interconnected pores between the particles. Because the ordinary flow just like the ordinary tube will go, but here a lot of particles, packing materials are there. So definitely the flow happen inside the between the particle void space. So what are the significance of the transfer phenomena here? Flow through packed bed governs here the movement and transfer, then movement and transfer driving force, velocity, and there is a pressure drop, then the heat transfer, mass transfer, and of course we can do reaction kinetics also. Then even we used to discuss the residence time distribution, that how much time the reactor staying inside that one. So the chemical reaction also we will discuss the residence time, space time over here. So these are the significance in the transfer phenomena for here. So now we discuss about the what are the packing material we use here. To understand the packed bed hydrodynamics, therefore fundamental for the design of numerous bioprocess equipment. So what are the common packing material here? Was a natural, the sand, activated carbon, all we use as a natural that one. So when you go for ceramics, so alumina pellets, then porcelain rings, we all use as a ceramic here. Then metallic packing material, we can use always stainless steel rings. So like that we can do for polymeric, then polypropylene beads, then polyethylene packing, this all be there. Then finally biological carriers, alginate beads, then chitosan, then polyurethane foam, all we will use as a common packing material for the packed bed. So what are the design properties here? It's a high porosity. If porosity should be a very high, then of course it's always come as a 0 to 1. Then it should large surface area should be there, then only we will get a more mass transfer here. So then the mechanical strength, very important, then high durability, then chemical inertness, it should not go react with something here, and definitely it maintain the low pressure drop. If whenever we maintain high pressure drop, is a very difficult to use this particle here. So what are the particle shapes? It's always like sphere, then cylinder, and sometimes rings, sometimes irregular particles. So these are the different type of the packing material inside the packing material, the shape of the material, which sorts the spheres and different things here. So, the laminar flow in packed bed, what are the assumptions for here? We already discussed it is a steady state flow. Steady state flow, we write dou by dou t equal to 0. Dou by dou t equal to 0, that is we called as a steady state flow here. Then is incompressible flow. Incompressible, compressible always will come as a gas. So, if you use incompressible, that is a one more assumption for here for laminar flow. Then is a Newtonian fluid, we know already tau equal to mu of dV by dy or dx whole power n. If n stands equal to 1, we call as a Newtonian fluids. If n is less than 1 or n greater than 1, it fall in the non-Newtonian fluids here. So, then there is the next one is a constant viscosity. Viscosity should be a throughout this one, it should be a constant. Then uniform packing, the packing is the uniform packing, not like random packing. It is like uniform packing, so that when you pass the whatever liquid or this one, it is always very easy to flow if you pack uniformly. So, there is no channeling, because when you pressure drop increase, then definitely the channeling occurs. So, you make sure that there is no channeling here, and the wall effects, sometimes the wall effect will be there, and we assume as a negligible wall effects, there is no wall effects here. And that is a creeping flow. Creeping flow is a always viscous force will be a more domination. So, sometimes we can say laminar flow, both are all same, the creeping flow or laminar flow, but this is a viscous force whenever dominant, then automatically the Reynolds number get decrease. So, that is only here also they mentioned Reynolds number less than 10, we come for as a laminar flow. So, Reynolds number we define as the dV rho by mu, that is called Reynolds number. The Reynolds number is always less than 10, is not greater than 10. So, then the viscous force dominates, that is correct, because the viscous force dominate. If viscous force dominate, then automatically Reynolds number goes decrease. If inertial force dominate, then automatically Reynolds number get increase. That is only here they mentioned the viscous force dominates, but the inertial force are very negligible here. So, these are the assumptions for laminar flow in the packed bed here. So, now we will discuss about the how the packed bed geometry we do here, and there is a container volume, that is a V. We always write V, that is a volume. Then volume occupied by particles, the Vs is the occupied by particle Vs, we called as this one, and then void volume Vv. So, we write volume, void volume. So, if I ask sometime what is the total volume here, total volume is the summation of void volume Vs, void volume, then what is the volume occupied by the particles. So, normally the void fraction porosity we write for epsilon, we always write epsilon, it falls only 0 to 1, it is not above 1. So, there is a Vv, void volume by total volume, we always write void volume by then total volume. So, what is the total volume? The total volume stands void volume Vv, then whatever the particle occupied, no, that volume also there, that we call as a total volume. So, Vv by V, we write epsilon. And then what are the typical values, or generally we use here the packed glass beads 0.36 to 0.40 we use as a porosity value, and then sand we always use the 0.30 to 0.45, sometimes the random packing 0.35 to 0.50. So, here the total volume is summation of the particle volume occupied with particles, then there is a void volume is here. So, next one is for say specific surface area, how we this one, it is a flow occurs over the entire surface of the particles. Hence, the surface area is very important because that gives the more enhancing the mass transfer, heat transfer, whatever. The specific surface area defined here, surface area by bed volume. So, what is surface area here? Surface area here by dp square, then other one is a volume for sphere, we will write for by dp cube by 6. So, there is a 4 by 3 pi r cube volume, then change this one, then finally we get that one pi dp cube by 6 here. So, then therefore, is the area here AP is a by dp square, then what is the value of this one? Pi dp3 by 6. So, then after this one we get, if ratio of area of AP by VP, we get 6 by dp after solving this one. So, sometime if it is, there is a void fraction you want to add here, then inside packed bed it is a 1 minus epsilon. So, whatever the solid occupies, because epsilon is a void volume, that is a porosity, then 1 minus S is the how much solid occupies by the volume. The same equation A, we can write 6 by dp here, the area of here A equal to 6 of 1 minus epsilon dp. So, that is the way we write A is the specific surface area here. The specific surface area AP by VP, that we can write A we can write A equal to 6 by dp. So, then what is the equivalent particle diameter? It is a real particles, it is a spherical. Then for irregular particles, what will happen when we have to do this for equivalent diameters, that is called dp, equivalent diameter dp. So, dp we can write 6 of Vp by AP, that is the volume of this one, then surface volume by area. So, 6 by Vp, then this is called as the surface volume equivalent diameter. We always write the surface volume equivalent diameter, then 6 Vp by AP. So, then next is what is the average interstitial velocity. So, we already defined the superficial V, we can write Q by A, because the Q is a volumetric flow rate, that is a meter cube per second, then area is a meter square. After solving we will get the velocity meter per second, that is the average interstitial velocity. So, however, this type of only the void fraction is available for the flow, but actual velocity inside the pores, that VA equal to, already V is there, V by epsilon, that is the porosity. So, this is called interstitial velocity. VI already we know what is the superficial velocity, this also we already discussed in the class. V is the superficial velocity divided by the epsilon, that is a porosity, we get interstitial velocity. So, then if the epsilon is 0.4, then the superficial velocity is here 0.01, then we will get a interstitial velocity or actual velocity here 0.025 meter per second. It is the only example for how we are calculating interstitial velocity here. Then we discuss about hydraulic radius. There is a packed bed as a represented as a small particle in the capillary tube, small capillary tube. So, we always say hydraulic radius. Hydraulic radius is the what is the flow area, the ratio of flow area by wetted perimeter. So, that is we write hydraulic radius here. So, for packed bed, the flow area void volume per unit length. For packed bed, we always write the flow area is the volume by per unit length, then automatically we get flow area. So, for wetted perimeter, the solid surface area per unit length. So, this is the difference for here. When you use wetted perimeter, the solid surface area per unit length, but when you use a packed bed, the flow area we call as a void volume by unit length. So, therefore, we can write RH here, RH equal to epsilon by A. What is that? This is A, then epsilon is the porosity. But already we know what is the area, this one, that is the A here, the 6 by 1 minus epsilon by dp, that we will use for the solid is here. So, then again you convert in terms of hydraulic radius, the same thing here, hydraulic radius RH equal to epsilon dp by 6 into 1 minus. You substitute here, see the A value here. So, you know RH equal to epsilon by A, then A we know, substitute, then we get a hydraulic radius that we called as a epsilon dp by 6 into 1 minus epsilon. So, Huygens-Poiseuille equation we already know, we will use for only laminar flow. There is a pressure gradient, we write lambda PL equal to 32 mu LV by GCD square. Already we discussed week 2 itself. So, the packed bed are treated as the millions of capillary tube, because so many capillary tubes are there. Then the equivalent diameter we write D equal to 4 RH, 4 RH a hydraulic radius. So, then we know the RH value, because we calculate from the previous one. RH here we calculate here, you substitute here, then the RH you substitute here, then we will get the what is the DE, equivalent diameter. So, once the DE know, you substitute DE here, this equation just substitute the DE, then you modify the equation, then we will get a new Huygens-Poiseuille equation for flow through packed bed. So, delta P by L equal to 32 mu, the VI is the interstitial velocity, because this is the ratio of superficial velocity by porosity, we call as the interstitial velocity. So, this equation you substitute V also, then the dA also. So, after the modification we get a beautiful expression delta P by L equal to 72 mu V by 1 minus epsilon square by this one. It is a flow through packed bed for laminar flow, we will always use the laminar flow. So, then we have to use for some Kozeny Carman correction, because the normal packed bed is not in the straight tubes, because it is always zigzag back, it follows the zigzag paths. So, then we have to introduce some additional correction factors. So, there is additional resistance also there. So, then we introduce a Kozeny introduce a empirical correction. So, some correction you have to use. So, the same thing you multiply with the 2.08, this equation you multiply with the 2.08, then we get as a delta P by L equal to 150 of mu V of this one. So, this always we will use for the Kozeny Carman equation for laminar flow. This is a laminar flow. So, we always use this one. So, what are the interpretation of this equation finally gives here, because we found the laminar equation, Kozeny Carman equation. It is a pressure drop when increases, definitely when viscosity also increase, that bed become denser, of course the particle diameter also decrease, the velocity also get increase. But the pressure drop decrease, what will happen, the particle diameter increases, the porosity also increases. These are the interpretation from the equation, the previous equation. So, then laminar flow in packed bed here, what are the effect of the force stretches on the pressure drop. So, first we take activated carbon, because activated carbon is a fine particle, fine porous parts we always use inside that one, it is interconnected micro channels. It definitely result extremely high specific surface area, because the packed material sometimes we always pack the activated carbon here. It is the best for the use for as a excellent surface area to use the adsorbent, biosorbent. Is this narrow the pore passage offer greater resistance to the fluid flow. So, then consequently the permeability of the bed decreases, then it is leading to the higher pressure drop across the bed. So, if we use the glass beads, what will happen here, it is a very smooth, of course there is a spherical particle if you use the glass beads, but it is a large interfacial void space are there and little low specific surface area. The surface area will be a low when you use this one. So, these larger flow channels always allow the fluid pass through the more easily, and the resulting higher, the permeability will be higher and the pressure drop will be a lower here. So, that is the difference of activated carbon than glass beads if we use inside the packed bed. So, what are the limitation of Kozeny Carman equation? It is a laminar flow, again neutral fluids, uniform particles, constant porosity, there is no wall effects and no channeling also, because if you use the laminar, and definitely these are the derivation for you have to use that one. So, when Reynolds particle less than 10, there were more viscous forces no longer dominant here if you use greater than 10, because so far we used as the Reynolds number less than 10, but when you increase the Reynolds number greater than 10, then we have to go for Ergun equation. The first one is we used the Kozeny Carman equation. Whenever if we increase this one, we have to go for the Ergun equation. It is applicable for the turbulent flow. So, what are the key takeaways today that we discussed about the laminar flow through packed bed? It is governed by the structural characteristics like a porous medium. We discussed the porosity, then the specific surface area, hydraulic radius and interstitial velocity. So, then we discussed the Kozeny Carman equation, that is definitely give the theoretical relationship of between the what is the pressure drop, then particle size, that is we discussed the porosity, epsilon porosity, then viscosity mu, then the superficial velocity also under laminar flow conditions. So, the pressure drop, what will happen? Pressure drop increases with increased viscosity and then flow velocity, it is a decrease in the particle size or porosity. It making the optimization of bed structures, then operating conditions is essential for the efficient packed bed reactor design. So, then so far we discussed laminar flow. When you use the higher Reynolds number, the Reynolds number will go high and automatically the inertial forces are mainly dominant and then the viscous force not dominant one. So, that is the higher Reynolds number here. Whenever go to higher Reynolds number, we can always we have to go use for Ergun equation we have to use. Thank you.